The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Now, to understand as to why each element has its own unique emission spectrum, we're first going to do a little bit of review, and we'll use the Bohr model for the hydrogen atom to do so. Looking at figure 4.5a, let's first point out some of the prevalent features here. We have our nucleus in the center here, and each of these orbits, as we see here, is identified by a principal quantum number. Now, we can think of these orbits or these quantum levels as being different energy levels, right? And each energy level here is associated with has its own specific energy associated with it. And we'll come back to the energies associated with the energy levels in just a moment. But for now, let's take a look at this electron down here. Now, as this electron here gains enough energy, absorbs enough energy, it can transition to the second energy level, as we see here, right? And in doing so, and as the electron can transition from the first, by absorbing energy from the first energy level to the second energy level, the electron can also release energy, right? It can also release energy to transition back to the lower orbit, And when the electron is in its lowest allowable energy state, as we see here, it is then said to be in its ground state. Now, for our electron here, that's going to be the first energy level, as we see here. Now, a few other things that we should note about electrons. Firstly, being that electrons, whether they're absorbing or they're going to be emitting energy, they do not need to transition sequentially to orbits. So what I mean by that is, if we take a look here, if we have an electron that's in n equals 1, it doesn't have to go to n equals 2, it can go from n equals 1 to n equals 3 or n equals 5, or even furthermore, right? The electron can, if the electron is ionized, as we see here, meaning it absorbs enough energy, it can leave the atom completely. Okay, now let's talk a little bit about the energy of the electrons. Coming back here to figure 4.58, the amount of energy gained or lost by the electron, right, has to be equal to the energy difference between the orbits for that electron to transition from one energy orbit to the next energy orbit, as we see here. Now, what that means then is that the electron cannot be right here in between orbits, and the reason being is the electrons don't build up energy. It's either the electrons are going to be able to transition to are going to be able to absorb or emit enough quantum energy, right, that they move to one orbit or the other. They're not going to be in between as such. And a common analogy used to illustrate this point is, if you think of a flight of stairs, you're either going to be on one step or the other. You're not going to be standing in between steps. Similarly, with electrons, they're going to be in one orbit or the other. Now, we'll just get rid of this here. Okay, now that we know that each one of these orbits has a specific amount of energy associated with them, furthermore, that electrons can either absorb or release energy to transition from one energy orbit to the next energy orbit, let's get back to talking about as to why we have a unique emission spectra for our elements. Now, if we take a look, we'll start from the top again. If our electron has gained enough energy, it's in the second energy level. Now, it's going to want to get back down to its stable ground state configuration, and in doing so, it's going to release a wavelength of specific light. Once again, it's going to release a wavelength of specific light. Now, another way we can say this is that the electron is going to emit a quantum of energy, and a quantum of energy is just going to be a discrete packet of energy, which corresponds to the difference in energy between the orbits or the energy levels. Now, a quantum of energy of light is what is referred to as a photon, as we see here. Okay, great. Now, to sum this up, as the emitted as we see here, as the emitted colors that are seen, right? They come from these quantum drops that are experienced, right? They come from these different quantum drops that are experienced by the electrons, and each quantum drop is going to have a different, and each quantum drop is going to have a different amount, is going to have a different quantum energy that is being emitted from the electron, or specific wavelength of light, as we see here. Now, if we come back over here for one moment, then that tells us, right, that the atoms, they're not going to have a continuous spectrum, right? Atoms are not going to have a continuous spectrum, but instead they're going to have a unique emission spectrum as such. And once again, why is that? That's because the atoms are constrained to emit quanta of only a few specific energies. Once again, those atoms are going to be constrained to emit quanta of only a few specific energies. Now, if we, generally speaking, this is why objects emit light. And what I mean by that is, if we take, for example, street light or just fire in general, as electrons are going to get excited, they go to a higher energy level, and if they go to a higher energy level, when they want to go back down to their ground state, they're going to release energy in the form of light. Now, if we come back over here, if we wanted to measure these quantum drops, we can do so through the following equation, and we'll do that in a few slides. But next, let's really take the ideas that we have built on the past few slides and connect them on the next slide.